Hi, thanks for joining me. Today I'm going to be showing you a cool integral video. We have in defined to be this indefinite integral here. It's the integral of tan x all raised to the power of n dx, and n is either a natural number or 0, so it's a non-negative integer. Now of course this thing here is an indefinite integral. What we want to do in today's video is build up a recurrence relation involving in. So you've seen recurrence relations before, for example with the Fibonacci sequence. You have fn plus 1 being equal to fn plus fn minus 1. So the next term in the Fibonacci sequence, the next term in the sequence is given by the sum of the previous two. We want to derive something that looks a bit like this, but with in instead. Okay, so we want to derive a recurrence relation on in. Now of course it won't be an exact recurrence relation because of course this thing here is going to have a plus constant. So for today's video we're just going to ignore constants completely and just try and get something without any constants in. But anyway, if you want to have a go at trying to derive a recurrence relation based on this, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so there are in fact a couple of different ways you can do this. The way in which you might think to do it, if you've seen something similar before, if you've seen, for example, the integral of sine x all raised to the power of n, or the integral of cosine of x raised to the power of n dx, you might think to do this by integration by parts, and that's perfectly valid. But in fact we can do this, because it's tan, we can do something different which actually makes this a bit quicker, I think, although it is fundamentally the same thing. What we're going to do is essentially use the fact that 1 plus tan squared of theta equals secant squared of theta for all theta. In other words, the identity 1 plus tan squared equals secant squared. Anyway, what I'm going to do is for now just assume that n is bigger than or equal to 2. And the reason for that is that the other cases are n equals 0 and n equals 1. When we have n equals 0, this thing here is tan to the 0 of x, so tan x all raised to the 0, which of course is 1, so that's just the integral of 1 dx, which is just x. Okay, and in the case n equals 1, this is the integral of tan x, which I can't remember off the top of my head. Annoyingly, I think it's log of secant of x, something like that. But it's something which we know, or we can look up in a table. But it gets interesting when we look at n bigger than or equal to 2. Okay, so let's jump right in. Let's write this thing here is equal to the integral of tan to the n minus 2 of x times tan squared of x dx. And you might be wondering why on earth I'm writing it like this. Well, I want to use the fact that 1 plus tan squared equals secant squared. So I'm going to actually replace this tan squared x here with the secant squared x minus 1. Okay, like so. And then what I'm going to do is use the linearity of the integral to write this as two different integrals. So this is the integral of tan to the n minus 2 of x dx. Times secant squared of x dx minus the integral of tan to the n minus 2 of x dx. Okay, so just bringing that into two different integrals. But if we look at this thing here, the integral of tan to the n minus 2 of x dx is precisely this thing here, except with n replaced with n minus 2. So this thing here is precisely n minus 2. Now, you've got to just be a bit careful, and that's why we had to insist that n is bigger than or equal to 2, because if we were looking at n equals 0, that would be I of a negative number, and we haven't defined in for negative n. So we have to insist that n is bigger than or equal to 2, and I justified that because we can already do the base cases n equals 0 and n equals 1. So this thing here, in minus 2, is perfectly well defined. So we've got in equals this integral here minus in minus 2. So we're starting to form our recurrence relation. Let me bring this to the top of the whiteboard and we'll continue. Okay, so we have in equals this integral here minus in minus 2. So we want to evaluate this integral here. It looks a bit ugly, but the key to this is noting that secant squared is the exact derivative of tangent of x. So this thing here is sort of an exact derivative, but to make that explicitly clear, I'm just going to be doing a u substitution. So let u equal tan x, and that of course implies that du is equal to secant squared of x dx. So this integral here, let me just call it j. We have that j is equal to the integral now, tan of x to the n minus 2 just becomes u to the n minus 2. Okay, and secant squared x dx is just precisely du, and this is a nice integral to evaluate. We can just, this is a polynomial, so we add 1 to the power and divide by the new power. So this thing here is u to the n minus 1 over n minus 1. And remember, we're just going to ignore constants for today. So that's that. And of course u is just tan x. So this thing here is precisely tan to the n minus 1 of x all over n minus 1. Okay, and we're basically done now because we can just plug in j back into this thing here. So we get that in is equal to tan to the n minus 1 of x all over n minus 1 minus in minus 2. Okay, so we've expressed in terms of this sort of function plus in minus 2. So if we wanted to work out, say, I of 6, we know that I of 6 is when we plug in n equals 6 into here, so it's tan to the 5 of x divided by 5 minus I4. But then we can use the exact same formula to work out what I4 is. I4 is tan cubed of x over 3 minus I2, and I2 is tan x divided by 1 times I0. And I0, remember, is just x. And I guess one other thing to notice is we've got to divide by n minus 1 here. But again, that's fine because this thing here, we were only focusing on n being bigger than or equal to 2. Anyway, that's today's video done. I hope you have enjoyed the solution. Thanks for watching. I'll catch you in the next one. Have a great day.